I definitely want to encourage everyone to ask questions. It's fine to interrupt with questions. If you do it in the chat, I may see it, I may not, but probably it's best to just interrupt politely and I'll try and basically we can do I have some slides prepared, but we can also kind of do a choose your own adventure. So if someone has questions about something, I can go off in that direction, right? And also I like seeing people's faces, so definitely encourage you to have your videos on as long as the bandwidth is okay. So let's see, what was I going to talk about? Earthquakes. Basically, we have a big machine here at Cornell that I built, and we can squeeze big rocks and we can make little earthquakes. When this whole thing ruptures, it's like a magnitude -2. The biggest sort of contained event we can get is a -2.5, and I'll talk all about that sort of stuff. But today I'm going to talk a little bit about what happens when we inject fluid into a fault. For some reason, I thought that y'all were interested in that because, I guess we're, you're not that far away from Oklahoma here, and you're in the New Madrid seismic zones. I thought maybe that'd be interesting. I think probably I don't have to explain too much to y'all that fluids are associated with earthquakes. The basic idea is if you put water in the earth, you can increase the fluid pressure there, and eventually that'll make its way to a fault, and it could trigger it. But it's actually, a lot more complicated than that. And I'm sure that, a number of people at CERI have worked on that. And so you've got like permeable layers, you've got fluids that make their way down into the crystalline basement. You've got aseismic slip, which could transfer stress. So this is sort of the thing that I'm going to be talking about. So we have these like natural observations of fluid-induced earthquakes. There's been a lot in Oklahoma, Arkansas, Texas. We also have sort of 10-meter scale experiments that have been done at a few places. This is Grimsel in the Swiss Alps. Basically you go down in a tunnel that was, made for perhaps some other reason, but then you decide maybe there's a fault that crosses one of these tunnels, and you drill a hole and inject fluid, maybe put in a seismic array and monitor what happens. So, in the real earth, where you can actually measure things. And then there's this popular paper here, came out in Science, gosh, almost, long time ago now, where they were actually able to measure like the fault opening and the fault offset when they're injecting fluid into a fault. And what they found is that there's a lot of aseismic slip. There's a lot of little earthquakes that are produced, but when you inject fluid into a fault, it doesn't just make a big earthquake, it can also just slip slowly or slip quietly. And that's an important one. And then the other sort of like key piece in this is there's a lot of numerical modeling. People have been trying to model those field studies. And basically, you have an injection point, maybe you set up some criterion for what causes the fault to slip, and you can see how as the fluid pressure diffuses across a fault, how there's going to be a slipping region and how shear stress could vary. And what I'll do is I'm going to show, if you increase time, like maybe the fluid pressure increases and the slipping region increases and the stress distribution changes. What I'm going to show in the lab is basically we can make conditions that are very similar to these modeling studies. And so a lot of what we see in the lab, when we inject water into this big rock is, at least it's consistent with the modeling studies. And then a few things that we see are, different. So that's sort of a point of comparison here. All right, so I am, I teach engineering. I guess I'm an engineer. And so I wanted to, I'll show a few pictures of how this machine was built. But basically, just to get us started with some motivating questions, what is the role of that slow slip? Like, what is it really doing? If you inject water into the earth and it causes slow slip, what does that do? What does that indicate? And then how actually does an earthquake start? Like, how does the dynamic part of the slip, the stuff that's going to cause the shaking that could be felt at the surface, how's that start? And what determines the magnitude of these earthquakes? We really don't want to have big ones. These questions are definitely related to more fundamental questions that I've been asking myself for 10 years or so. How do earthquake ruptures start? How do they stop? What's the difference between a fast and a slow earthquake? So I'll be talking about a big rock. I want to put it into the context of like, why are we doing a sample that's so big? A lot of rock mechanics happens on small scale samples, little hand-sized samples. And if you've got a small sample, you can put it in a pressure vessel and you can get it up to pressures and perhaps even temperatures that are realistic of what we would expect in the crust, right? Maybe 100 MPa style pressures. But the issue with the small sample is because rocks are kind of stiff, it kind of just behaves as one point. Like it's one point on a fault that it either is slipping or it's not slipping, and you can measure the friction, but it's just sort of like a single point. And so if you want to get that rock to slip really fast, and we think that when earthquakes occur, the faults slip very fast, you really have to like load it with a motor or a fast acting clutch or something in order to get it up to those high slip rates. And then what I've been working on is these larger samples, these meter-sized samples. Now we're not able to get up to the pressures that we would want to be more, I'll be showing you experiments at 4 megapascals, right? So this is like not even a kilometer deep type of pressures. But the advantage of the big sample is that the sample behaves more like a continuum. It's not just a point. One part of the sample can slip and another part of the sample doesn't slip. And so the sample can kind of load itself. If one part of the sample starts to produce dynamic rupture, the other part of the sample is going to get hit by a dynamic rupture, and that causes it to actually get loaded orders of magnitude faster than you could even load in the fastest high-speed loading machine on a rotary shear machine, for example. The other thing is you can see sort of like the spontaneous initiation of dynamic slip, which isn't really, you can see that on small samples, but it's controlled by the loading machine rather than the properties of the rock. So I was I'm an assistant professor at Cornell. My first couple of years, I built this machine. We got a bunch of steel trucked up from Philadelphia. We put it in the lab. We plumbed a bunch of hydraulic cylinders. Here's the samples. They're berry gray granite. They're from Vermont. They're basically just big blocks of rock. You can actually see this little trough that's been cut in one of them. And there's a little tiny hole you can barely see here. That's what we're going to be injecting the fluid in through, as these little holes that were pre-drilled in the samples. We put the machine together. This is what it kind of looks like when you look down at the top. It's got these arrays of hydraulic cylinders. This is a lot here. So each one of these little yellow things is a 100-ton cylinder, so 200,000 pounds. This is a 32 meganewton loading machine. And it's biaxial, so you can do 16 meganewtons in the other direction.
Can I ask you a quick question?
Yes, please.
Do you have a certain procedure to check the quality, initial quality of those samples delivered?
I don't. I just, yeah, good question. So it takes like a very special tool to be able to check the flatness of these, because we really want them to be flat so that they're really mated. But what we did is we put them in the machine and we just grinded them past each other, and we tried to see how much it's wearing, and there was definitely an initial run-in period, but after we slipped it for like 15 millimeters, we took it out and you could see it was being polished. It was being polished everywhere. There's this one place where the trough is, and the mating surface on the other sample was not being polished because it was a gap there, and everywhere else was being polished. So it's very good quality control. But something like 15 microns is sort of like the variation in overall waviness of the sample. Now, over time, there's been kind of like grooves and scratches that develop and some powders build up. But yeah, it's pretty good quality control for the length scale. Turns out it's not that hard to order a big old rock. You know, they use them for foundations for sensitive physics equipment and stuff, and then also for building facades and stuff.
May I also ask a question?
Please.
All right. Sorry for interrupting, but are your blocks asymmetric in mass?
Yeah, they're asymmetric. There's basically a moving block here. It kind of moves. And then there's a stationary block. The moving block is bigger. The thickness is the same.
Maybe, since I'm not an expert in these machines, why you made it asymmetric?
I had my own reasons. I wanted to be able to do seismology on this block and have it be like a long time before reflections would come back. So I wanted at least one of the two blocks to be like as big as possible. But I think that asymmetry actually causes some weird stress states, which ended up being like a fortuitous thing, because with weird stress states, we can actually get ruptures to stop within the sample. So I had some reasons, maybe they weren't the best reasons, but the other reason is we needed a lot of cylinders to push on this rock. And so I needed this rock to be as big as possible. So I had a large pushing area.
Right. So there is technical reasons.
There's technical reasons.
I wonder if that so that's basically a fault that is asymmetric in mass, and I wonder if you see that in your results somehow on the rupture. So that's why.
Okay, so that's a good question. So if this thing starts rupturing, it's going to start slipping on this interface here. And the time it takes for the waves to get to the other side of the sample and back is much longer than it takes for the rupture to go down. So that asymmetry probably doesn't affect the dynamic rupture propagation in any way. The samples are big enough. If they were very thin, then you would get reflections that would affect the sample. But essentially, the rupturing interface does not know the mass of the rock because the stress can't propagate there and back fast enough.
Okay, thanks.
There's no inertia at that point. All right, so the way this machine works is very simple. It's like as simple as I could dream up, basically, and that is the line of cylinders here. Just squeeze the two samples together. We measure the pressure in that line, and that's the normal stress. We close a valve and hold it roughly constant during the experiment. And then we slowly increase the pressure in this array of cylinders, and that causes the top block to translate relative to the stationary block. And it also translates on an interface here with this yellow dashed line that's behind the cylinders, and that's a Teflon steel low friction interface. So the top block just sort of translates, and it can move about 50 millimeters before we have to pick the sample up with a crane and reset it. And so this is the procedure we do, is we hold the normal stress constant, we increase the shear stress, and then when the block slips, when the dynamic rupture happens, the sample average shear stress, which is shown in black here, decreases, and we get a stick slip event. And then we just keep loading it up and we get more stick slip events. The questions are great, by the way. I love it. I can handle them, and it makes it way more interesting. So one of the cool things about this big rock is we can get it so that part of that fault, 3 meters long, 0.3 meters deep, ruptures and slips, and the other parts of the sample don't slip. And that's something that's pretty unique. It's only ever been done before in plastic and at the USGS back in the 80s using fluid injection, actually, like one paper. So we do this routinely, and so that allows us to study why do these ruptures stop, which is pretty cool. And I'm going to show some examples of what those results look like. Basically, we have a line of sensors going down the sample that are local slip sensors. They're an eddy current displacement sensor. The probe here is glued to one of the blocks. The target is glued to another block. And when local slip occurs, a little gap opens up between the probe and the target. So we can measure slow aseismic slip this way. We can measure rapid dynamic slip this way. And we can measure the distribution of slip along the interface at 16 locations. So what I'm going to do is I color code the slip sensors on the side we're pushing on is the red end, the other side's the blue end. And then on the left here, you can see what the output from those eddy current sensors over time is. So this is just about a 1 second time interval around one of these slip events. And you can see that the red end started to slip kind of slowly. And then suddenly there was this really rapid jump. And a bunch of different slip sensors saw a huge jump in slip. This one slipped 35 microns. Some of them slipped less. And then after that, it kind of didn't slip at all. And then the blue end didn't slip at all ever. And so the plot here is, I call this a pink-purple diagram, is plotting the exact same data, but is plotting it differently. It's laying down snapshots in time and it's showing the distribution of slip at any given time. So this slow slip that's happening only on the red end is showing up as really closely spaced contours. And I'm color coding those contours so that they like cycle between light pink and dark purple, like every 50 milliseconds. So this color banding, the pink and purple color banding, is demonstrating very slow fault slip. And then when the individual contours separate here, that's super fast slip. It's slipping, and I'm laying down like a contour every 200 microseconds or something like that. Let's say it says here, snapshots every 1 millisecond, color cycle every 50 milliseconds. So this is the dynamic slip. This is the slow slip. You can see where it's located along the length of the fault. And you can see that the final slip distribution, which is this black line, it really stopped slipping about 2 meters down. And this last meter of the fault didn't slip at all in this particular slip event. And this slow slipping region that we have here, it's about 1 meter in size. And people like to think of this as a nucleation length. It's like there's this idea that for a dynamic rupture to begin, you kind of have to have slow slip in a region that maybe expands and then it reaches a critical length scale, and then it can go unstable. Because a larger crack is essentially has a lower stiffness, and so you can actually get instabilities with larger cracks. It's kind of the same idea as a Griffith crack in mode 1 fracture dynamics, but this is in a mode 2 fracture. And so we can kind of measure this length scale in the lab, and at 4 MPa stress levels with these granite blocks, it's about 1 meter. Here's some different examples of sort of like imaging the initiation of rupture for a few different events. So here's different pink-purple diagrams. This is one where we were at 10 MPa of normal stress, and that nucleation length scale is a little bit smaller, which is consistent with expectations. Here's an event that's completely confined within the sample. So it still nucleates at about 2 meters here, and then it starts to slip faster, but it never ruptures at 3 meters, and it never ruptures between 0 and 1 meters.
Greg, sorry, I have another question because this is really interesting. How long is the blocks that you have over there?
They're 3 meters long.
So the critical pad size is 1 meter. So if you don't have 1 meter, you don't have enough stress at the rupture front to go to propagate farther. Is that what happens?
If you don't have 1 meter, then the stick slip events will initiate because of the compliance of the loading frame and not because of the compliance of the rock. So the instability criterion will be dependent on your loading machine. So that's why we have a 3 meter rock, right? Because we want to be able to see this initiation and get it to sort of like spontaneously rupture on its own based on the elastic strain energy stored in the rock, not stored in the steel loading frame.
Okay, thanks.
This example on the right here shows that it was actually creeping, like slow slipping for about a little over 1 meter. And then in this case, it nucleated right at the transition between the creeping and the locked section, which has been seen like for decades actually in numerical simulation. The other thing I want to point out, if you've got one of these confined slip events and you just look at the slip that occurred, between the beginning and end of the event, and there's this distribution of slip, there's also a distribution of shear stress changes that we can measure with strain gauge pairs that are located at many locations along the fault. And so what we can see is that the local stress drops in the region that slipped, and it actually increases on the edges of that. So basically we have a little shear crack, stress drops within the crack, and it increases right outside the crack. And then far away from the crack, it doesn't do anything, no changes. This is what the machine looks like a little bit closer to today. We've got a lot of stuff on it. And then we've got these 3 holes in the rock, which we use as fluid injection ports. And this work that I'm going to be presenting today is predominantly done by my PhD student, Sarah Beth. So I'll try and do my best to present her work as well as I can. So what we do is we inject fluid into this little hole here. That gets piped down into the rock, and then there's another hole that pipes the fluid directly into the fault. Okay. And okay, that's pretty cool. And so we can draw pink purple diagrams from events that occurred due to fluid injection, and sure enough, they nucleate right where we're or they're slow slipping right where we're injecting fluid, and then they go dynamic from there. Okay, but with fluid injection, we can do some things that are kind of cool. Typically, when we load the sample, we're just squeezing it from the exterior, and it just makes a slip event when it wants to make a slip event. So here's like, these sort of diagrams saying like, okay, it reaches some critical stress level, then it slips and it goes down, the stress is dropped. It reaches a critical stress, it slips again. What we did here is we explored 3 different cases where we reloaded the sample up to pretty close to the critical stress level, and then held that constant and then injected fluid. The middle case is where we increased the stress only a little bit, so it's a little bit lower than it was before, and held that constant and injected the fluid. And in case C, we actually reduced the stress level below where it ended up after a stick slip event, and then injected fluid into this lower stress environment to see what would happen. So we can actually initiate earthquakes at different levels of background shear stress. And then when we compare these 3, here I'm showing the fluid pressure that we measure in the well. Here we're injecting at a constant rate, 10 milliliters per minute. So the pressure is going up. And then what happens is the fluid pressurized region gets all the way to the top and bottom of the sample, and it starts to leak out. So we get a little drop in pressure, and then we just keep pumping, and the pressure pretty much stays constant. And then these lines here are showing the shear stress. So this is the case where we've got high shear stress. The green one is medium and the blue one is low. And we're plotting the 3 experiments on top of each other for direct comparison. And when the shear stress is high, it's only a couple seconds after that peak injection pressure was reached that a dynamic rupture event happens, and it blows through the entire sample. And that's what this drop in stress indicates. And when the shear stress was low, we had to pump and pump and pump for about 500 seconds. And we expect that the fluid had to sort of like, it's leaking out the top and bottom, but it's still expanding along the length of the fault. And eventually we got a dynamic rupture. And it didn't go through the entire sample, it just ruptured part of the sample. And the medium case is sort of in between, right? We can not just look at those changes in overall sample average stress, but look at the local slip that's occurring for the 3 different cases. So this is the 3 slip sensors that are pretty close to where we're injecting it. And you can see that, in the high stress case, it slipped a little bit more and a little bit faster, and then it slipped a bunch when the dynamic rupture happened. In the medium stress case, it didn't slip quite as much. And then we got this slow slip event here, and then dynamic rupture at about 15 seconds. And then it's slipping, but the extent of the slow slipping patch is smaller at the low stress region or at the low stress case, and it takes a lot longer. We can plot that same slip data differently. Now I'm plotting, this is the distance along the sample, this is where we're injecting, and then the colors are corresponding to the log of the slip rate imaged by this array of 16 slip sensors. So you can see in the high stress case, the slow slipping patch was expanding pretty quickly. And you can see these little perturbations, like these little like sudden increases in slip are slow slip events, and they're showing up as these yellow bands. And so we can see that at higher normal or at higher shear stress, the slow slipping patch expands faster, and slip occurs earlier. And then the other thing to notice is that the shear stress, which I'm showing now, this is the output from those strain gauge pairs in black. The local shear stress is dropping in the locations where it's slipping and where we're injecting fluid, and it's actually increasing in the surrounding part, similar to what we saw, for these confined events. Basically, we're making little confined, slow slipping regions that are behaving the same way as we saw before, where the stress is dropping within the slipped region and increasing in the surrounding part. In this slide, I'm showing the three cases at the same time scale. And in this slide, I'm showing the same three cases, but at different time scales. So this like A2, B2, and C2 is the dynamic rupture event that happens. And for the low stress case, that happens after about 500 seconds. And you can see in all three cases, we get these slow slip events that are occurring. And then we get dynamic rupture. And in this low stress case, the dynamic rupture, it only ruptured like part of the fault. You can see the stress actually increased at a lot of different locations. And that's indicating that the dynamic rupture was being stopped.
Greg, can I ask a quick question?
Yes, please.
Do you know what the permeability of the granite is? The fluid just propagates along the fault, right? You don't have any, the sample doesn't get wet, so to speak, right? You don't have any the rock sample.
Yeah, great question. So we did try and inject at a really slow rate one time, and all of a sudden the granite started to behave like a permeable material. But in general, we're injecting pretty fast, even after 500 seconds. Granite's not really getting wet. It's just like a two-dimensional plane that the fluid pressure is migrating on. It's just migrating along the surface, or at least that's what we're modeling. And I'll show that modeling in just a couple of slides, because we can estimate the diffusion coefficient for the fault. Okay. We can estimate the extent of the pressurized region and stuff like that, right? All right, so I'm showing the data, and then what I'm showing here is that right before the dynamic rupture occurs in the three different cases, I'm showing how much slow slip had accumulated and how much shear stress changes had accumulated. And what we see is that for the low initial stress case, it took a lot more slow slip and a lot more shear stress changes had to occur before a dynamic rupture occurred. So it didn't take as much time at high stress, and it took a lot longer time, more slow slip, more stress changes, more stress redistribution before an earthquake occurred. And then the blue line is our modeled fluid pressure on the fault, the distribution. And what I'll show is that at the low normal stress case, it seemed like the aseismic slipping patch was pretty much matching where we think it's being pressurized by the pore fluid. But in the higher stress cases, the slow slip is outpacing the fluid pressurized region. Here's the model that we're using to try and model the pore fluid pressure. There's this trough that's cut in the block. You can kind of barely see it here. And what we did is we injected water into this place where there's a trough, and we performed a shut-in test. So basically, we injected fluid in at a constant volumetric rate. The pressure was increasing, and then we just stopped injecting, and we just let the fluid pressure diffuse along the fault, over 50 to 100 seconds. And then we created a finite difference model of this process. So, and what we do is we impose in the model on this trough, we impose the pore fluid pressure that we measure until the shut-in, and then we just let the model do what it will, and just impose symmetric boundary conditions there. And we model it with different alpha coefficients, different diffusivity coefficients. And so we can just match the observed pressure fall off with the modeled pressure fall off and find that alpha of 10 to the negative 5th meters squared per second is sort of the fluid diffusivity that we can expect for this interface. And we can use that to map out the pressure distribution that we would expect at various times during these experiments. And so we can see that in case C, where it took 500 seconds for the slip event, that was enough time for the fluid pressurized region to actually expand, and it's tracking the slow slipping region pretty well. Whereas in the cases where the dynamic rupture happens after just a few seconds, the fluid pressurized region is still quite small. The region where we've got megapascal fluid pressures is tiny, and it goes out from there. So just to sort of summarize what these observations are, is well, in all three cases, high, medium, and low initial shear stress, fluid injection always triggers slow slip. And that slow slip included these oscillations, these slow slip events, basically like failed nucleation attempts. Like it was like starting to accelerate and then it kind of died down. Oh, and I forgot to mention, those slow slip events were sometimes associated with a pretty rapid expansion of the slow slipping region. So you had like a region that was slow slipping, and then you had a slow slip event, a sudden acceleration, and all of a sudden the slow slipping region expanded, beyond what it was before. And that slow slip causes a redistribution of shear stress, basically drops the shear stress in the part that's slipping and piles it up on the neighbors. Now the differences are at high initial shear stress, that slow slipping region grew faster and it outpaced the fluid pressurization region, and less overall slip and stress redistribution was required for dynamic rupture to initiate. And when the dynamic rupture occurred, it just blew through the entire sample. At low initial stress, the slow slipping region pretty much matched the fluid pressurization region according to our model, and much more slip and stress redistribution were required to get a dynamic slip event to occur. And when the dynamic slip event did occur, it was contained. It kind of blew a little bit further, but it didn't rupture the entire sample. And actually, all those results, except for maybe these slow slip events that are occurring within the slow slipping region, these have all been pretty well modeled. Like the faster expansion of the slow slipping region at higher shear stress, all this stuff has been, is pretty consistent with models. And it sort of paints this picture. Now I'm going to start to think about fault mechanics according to this sort of simplified linear slip weakening relationship, where you've got an initial stress, you've got a peak strength, and you've got a residual strength. And if the stress level exceeds a peak strength, that means it's going to start slipping. Some additional criterion is required for it to slip dynamically. Maybe you have to have a nucleation length scale or something like that. And then what ultimately is driving or fueling a dynamic rupture is the difference between that initial stress level and its residual strength level. And so this is our little schematic diagram of the two different cases, where in the high initial stress case, the initial stress was higher than the residual strength. So there's fuel for rupture. So all you have to do with fluid injection is get a dynamic rupture to initiate. And once you do, it's just going to run. And then it's either got to propagate into a region where the initial stress was lower, or it's got to hit some sort of a barrier like a fault bend or something that stops the rupture. In the low initial stress case, the initial stress is below residual. So the fuel that's available for rupture is only due to the stress redistribution that happened due to slow slip due to fluid injection. And then the other thing that happens is not just the dynamic rupture gets fueled by this stress, but actually the slow slip itself is getting fueled by the initial strain energy in the rock. And so that's why the slow slipping region can outpace the fluid pressurization region at the high initial stress case. Here it more closely matches. Now, there's some things in these experiments that don't really make sense, and they cannot be captured by the currently available models. I showed these cases here. There's like, I'm highlighting like event A1, B1, and C1, and that's a slow slip event that occurred in the 3 different cases, and then the dynamic rupture event in the 3 different cases, and I'm showing the pink-purple diagrams. What doesn't make sense is, why did event A1 occur? Why, under high initial shear stress, did this slow slip event occur? It's like starting to accelerate, and then it didn't go. Like there's plenty of fuel to carry dynamic rupture. We know that because just a few seconds later, a dynamic rupture just blew through the entire sample. So how come a local acceleration occurred and it died? It suggests that we don't really know what's going on with new earthquake initiation. Like the criterion to spark a dynamic rupture is not very well defined, and it's complicated. The other thing that doesn't make a lot of sense is, at the low stress, we did get dynamic rupture, but when it finally did occur, it's not like we had this gradual acceleration of slip like you would expect from classic earthquake nucleation model. It just sort of decided to go dynamic. It makes sense that there was enough fuel available. There's, the stress had been redistributed enough that there was enough fuel available to drive that rupture. But it doesn't make sense why it suddenly decided to go dynamic at, this 500-second mark. We didn't get a lot of warning, basically. And I think sort of the takeaway message here is, like, this rupture initiation process, the dynamic rupture initiation process, is very complicated, and it's very sensitive to small details in the fault, in the faulting environment. I've been studying it for a long time, and there's still confusing aspects. Okay, so I want to stop there and open up for questions. I do have other things I can talk about. I know we've got 20 minutes left on the hour. I can talk a little bit more about like the seismology we can do in the lab, and the type of radiated waves that are radiated from the fast and the slow events. I can talk a little bit about why ruptures stop in the lab, and other topics. But I want to sort of open up for questions and discussion and see where it goes.
Yeah, Greg, that was really interesting. So I'm thinking about this C2. Do you have any guesses what's going on? Is somehow the nucleation process affected by the background stress state? So I guess your observation is that you don't see any sort of gradual nucleation, right? Which is kind of puzzling. So I guess different from this A1 to A2 or something like that. It just, I mean, could it be that the nucleation process is below your what you can detect? That there's some small acceleration of aseismic that turns dynamic. Although it would be puzzling, right? I guess you would probably predict the opposite. The higher the stress state, the more the smaller the nucleation.
Exactly. Exactly. You would expect the opposite. If you have to inject a ton of fluid and you're at a low effective normal stress, you would expect a much larger and slower nucleation process, right? You can see, you can kind of see it was slow slipping a little bit, and the half second before this thing went, and it accelerated out of the edge of it, kind of similar to what's going on here. But essentially, the fault's behaving a little bit more brittly in this case than it was here, meaning that it didn't take as much deformation for it to really go unstable. I don't really know exactly why. I will say that this is not something that's unique to injecting fluid in the rock. All we have to do is like impose a hold, and we can get that nucleation process. So like if we're loading the sample and it's making events pretty regularly, if we just like wait and just pause that loading for 100 seconds and let the fault kind of heal and then reload, that'll shrink the nucleation process just as much as we've seen here, or even more. So it may have something to do with like the effective loading rate, or the amount of healing, or essentially the state of the contacts on the fault. that's happening here, you know, relative to the other cases. But my takeaway is like, don't think you know what's going on when it comes to this initiation process. It can initiate in places where you wouldn't expect, and it cannot initiate in places where you would expect it to just be able to go quickly.
Maybe it's the geometry of your fault. I mean, it seems like these characteristic distances are the thickness of your slabs, and that maybe the fluids leaking out of the top and the bottom create sticky zones or something that control that dimension.
Yeah, that's a good point. We can see a variety of nucleation styles given a uniform thickness. So, you know, the thickness of this sample is 0.3 meters, and so we can, you know, basically when the nucleation process gets smaller than about 0.3 meters, then yeah, it's hard to see exactly what's going on. But I'm pretty sure that the nucleation process that we're imaging is, it's not like we're only seeing nucleation length of 1 meter because of the sample thickness is 1 meter. I don't think that's an issue. We've done some experiments where we put slip sensors on the bottom and the top and see like what's happening differently on the top and the bottom, and like how would you, if you saw the same event initiate from two different perspectives, like what are the differences? And you can see some minor differences. But your second point though about the fluid, kind of like, you know, we do sometimes observe like fluid fingering and stuff, and if there's like a groove or something on the fault, maybe the fluid can propagate more rapidly through, you know, at some parts, and maybe like wrap around certain sections and cause stress concentrations that could then go dynamic in a different way than you would expect from a homogeneous model. That might be one of the reasons why we're seeing this type of sensitivity.
No, I would be. I was just going to say I would be curious to see a little bit about what you observed in terms of rupture arrest. I don't know how everyone else feels, but if we still have a few minutes, that would be quite neat.
Yeah, I agree. I also had that question, but I'll let him talk about rupture arrest, which I think it's more interesting than my question. So let's go on.
Let's see. Let's see if I can get there. Ground motions, rupture arrest. All right, so how do we get here? Okay, so the rupture arrest part is done in collaboration with my former student Huey Ke and Dave Kammer. So we've got these confined events, and so I showed this example before of like the distribution of slip and then the distribution of shear stress changes. And kind of there's two ways to get ruptures to arrest, in my mind at least. One is you have to like, the rupture has to propagate into like a barrier or something, like place maybe like some intact rock where there's no fault, or there's a jog or something, high strength, high fracture energy. Or you have to run it out of gas. Basically, you have it propagate into a region where the initial stress is so low that it basically has no fuel for rupture. And in our experiment, the only way we can get ruptures to stop is the second way. You have to run them out of gas. So when we set up these, when we get these confined events, we're setting up conditions where it's highly stressed and favorable to rupture at this one spot 2 meters down, and it's not, doesn't want to rupture. Like the initial shear stress over normal stress ratio is low here. So that's sort of one point. And then the other thing is my student Huey, former student, he looked at this very carefully, and he mapped out these stress distributions, or the stress change distributions associated with these slips. And there's kind of this at first you might think it's not very intuitive, but there's this one data point here. Like there's the part within the ruptured region that's dropped stress. There's the part outside the ruptured region that's increasing stress. And there's this one data point here that's sort of like a transition point. And you can see it here. And you can see 2 data points here and another one here. And we're sort of thinking about this a lot, because what that data point tells us is it tells us about how an arrested earthquake, how its slip profile or how its slip distribution tapers off. It's not elliptical. If it was an elliptical crack model, you would have an instantaneous transition from the drop to the peak. And here we're seeing this sort of transition region. And we were like, well, what is this thing? So we call it the earthquake arrest zone. It's the place where the earthquake wants to stop. And then we wrote a paper about it, which is published in GJI last year. So we were thinking about this rupture arrest thing. And we were talking about the arrest zone. And we were thinking, well, geez, if we look at this, if we plot out the stress changes associated with these confined ruptures as a function of slip, we kind of get something that looks a little bit like a slip weakening curve. And so we're saying, well, maybe this arrest zone that we're looking at is related to the cohesive zone, which is sort of related to fracture energy, which is like how quickly the strength evolves from a peak strength to a residual strength. So are these things related? And so we did the calculation, based on some experiments that we estimated, like what this cohesive zone length should be for our rock, and compare it to the arrest zone that we're measuring. And we found that they're off by more than an order of magnitude. So we're like, well, maybe they're different. So we set up some numerical simulations. Dave Kammer is into numerical simulations, so this is working off of his code. And so what we did is we set up numerical simulations to sort of model what we thought was happening in the lab, where we put in an initial stress distribution that's above residual strength, one part, and that's the part that's like favorable for rupture. And then we sort of taper it off so that the rupture is going to want to stop. And we were going to try and figure out if we could see the difference between the arrest zone and the cohesive zone. And so let's see if I can get this. Man, the animation is not very good. Let's see if we can get it to go. So we make these dynamic rupture simulations. And so we're sort of like plotting out how the slip profile is developing, and how the stress changes are developing, and how the absolute stress levels are developing. And we put this is a boundary integral method dynamic rupture simulation, and we put in a specific friction law with a slip weakening distance of 1 micron. And if you look at the absolute stress levels, that's what shows up. But if you just look at the stress changes, we get this huge, it looks like a slip weakening distance, but it's not. It's due to the fact that this thing was propagating into an unfavorably stressed region. So then we were like, maybe the way that an earthquake stops looks like high fracture energy or something like that. And so we set up a bunch of models. We made 3D models with different profiles of initial stress, and we calculated the moment rate functions from those and spent a long time making these models where the rupture is going out and stopping, and this little circle is the favorably stressed patch. And we made a bunch of models that we estimated from the models their rupture areas, their average slip, their stress drop, their moment, their radiated energy, and from that, their apparent stress. And we got a set of models that basically were self-similar. We made a bunch of models. Some of them were small, so they have this patch of favorably stressed region is kind of small, and some of them were bigger, and we used the exact same nodes in the resolution of the numerical model and this exact same artificial nucleation procedure for all of them. And we imposed the same fracture energy for all of them. We have the same slip weakening relationship. And we looked at this and we found that if you calculate the seismically observed fracture energy from Abercrombie and Rice for these different models, that seismically observed fracture energy scales, even though the actual fracture energy in the models is constant. And so we were kind of thinking that this observation that people have made, not even starting with Abercrombie and Rice, but definitely Abercrombie and Rice, 2005, worked on this a lot. And, Vieska and Garagash and others have worked on this, that this observation of fracture energy actually doesn't have a direct relationship to the fault constitutive behavior, to the actual fracture energy, that it's actually an indication of the overall rupture style. And in our simulations, at least, the reason we get this scaling is because of overshoot. And Abercrombie and Rice actually talked about overshoot when they first presented their idea of how to calculate fracture energy from seismic parameters. And they said, it could be a problem, but we don't think it is, so they dismissed it. But at least in our models, that overshoot is there. And so if you do have a little bit of overshoot, and the overshoot is scale invariant, and that's what we see in our models, then you end up seeing a seismically observable fracture energy that scales. And even though the actual fracture energy is much smaller and doesn't scale. So basically we're saying this has been interpreted a little bit wrong, and we should relook at this differently with the study. And then this study actually just came out last week. So it started out thinking about like how earthquake ruptures stop, and it ended up turning into like how fracture energy might scale. So that's my 5-minute spiel on that. But I know it's that's a lot. I've been trying to like do some publicity and like talk to PR people at Cornell about this, and they're like, so what is it? Why is this important? Yeah. But basically people have been saying that large earthquakes should have a fracture energy in the like 1 megajoule per square meter, which would imply that you have to have some additional weakening process that kicks in at large earthquakes that doesn't happen at small earthquakes. And so people have been saying maybe thermal pressurization and stuff. And what we're saying is, no, all you need to have is an earthquake that overshoots a little bit, and you can get this scaling. And it actually helps resolve some kind of issues, which is that sometimes people measure this seismically observed fracture energy and it's negative. And that's physically impossible. And maybe the data is not so good, and so they threw it away. But what we were saying is if you did have a negative one, that would indicate undershoot. And that might be an indication of a pulse-like rupture. And most earthquakes are probably crack-like, and they have this apparent scaling. And that if you had an earthquake with negative apparent fracture energy, that would mean it's pulse-like and has undershoot. So don't ignore the data. Maybe it actually means something. But this all came from the lab experiments that basically showed that in order for us to get a rupture to stop, it has to propagate into an unfavorably stressed region.
So I'm really dying to ask, can you predict the seismic pulse from your fracture pulses?
Tell me what seismic pulse and fracture pulse means.
So the far field P wave, for example, does it? Can you reconstruct it by looking at the distribution of slip on the fault?
From the lab experiments or from the models?
From the lab experiment.
Yeah. So that's hard to do because we're so close to the we're so close to the sample basically, or to the rupture, that basically we're not far enough away for P wave to separate from S wave and like a million other reflections off the edges of this sample. So the duration of rupture for one of these complete rupture events is maybe 8 milliseconds, which seems short, but that's a long time. That's enough time for like, waves to bounce around a lot in the sample. So what we end up getting, if you kind of just look at raw seismograms from one of these events, is you get P and S and PP and all these reflections just sort of like smashed up against each other. And the total duration of the event is much larger than the separation between the different phases. So you can't get it directly, but you can estimate the source spectrum of these events. And that's what I've done with my former student, Bill Wu. Basically what we do is we drop a ball on the sample, and the mechanism of the ball is different from the mechanism of the shear event, but all the reflections and stuff are going to be similar enough so that we can essentially use the ball as an empirical Green's function. And then from these observed waveforms, we can back out the source spectrum of the events. So we can't see like a P wave pulse, but we can, we throw away phase, but we can see the source spectrum through this technique. And that's how we're able to show that the fast events that we get, they're pretty well modeled by a Brune model with a corner frequency and omega squared fall off. And the slow events are different. They're depleted in energy right around that corner frequency. Did that answer your question at all, or?
Oh, a bit. Yeah, thank you.
Greg, is the setup you have in your machine fixed forever? Or you can, for example, study by material interfaces?
Yeah, we can study different things. The samples are big and heavy and expensive, but there's no reason why we can't try different things.
What about
yeah, go ahead.
What about further increasing the normal stress? So it's pretty limited currently.
Yeah.
So is it like economical reason, or is it technically?
All right, so I designed this machine to go up to like 20, 25 MPa. You can't go much higher than that before the fact that you're only biaxial starts to be a big problem, right? We're not confining the sample up and down. So if you go much higher than 25 MPa, you'll start to get the rocks falling. And so you'll ruin your sample. I have a smaller machine, like I have a 1/4 scale version, a picture of it somewhere that's kind of cool, but yeah, I don't have it. But on the small machine, we took the sample up to 20 MPa, and it's really cool. I mean, you do get more interesting like foreshock behaviors, and it's easier to get. Yeah, here's the comparison. Here's the small scale, and here's the big one. We took this one up to 20 MPa, and yeah, it damages the samples. So I wanted to do a bunch of experiments on this one before damaging the samples, because actually it's the same rock we've been using for about four or 5 years now, before going up to 20 MPa. But yeah, before before too long, we will take it up a little bit higher stress, but we will eventually be limited by the capacity of the machine, which is around 20, 24 MPa, and then the fact that the granite's just going to start to crumble.
But doesn't that imply that the behaviors you are observing at this low stress level can actually change when you increase the normal stress magnitude?
It can change, yeah. Yeah, so we change too much, right? I guess when I say like we started to get more interesting behavior at 20 MPa, we get these little events that at low normal stress are kind of small, but at 20 MPa, the little events are strong enough that you could actually see their stress changes on the strain gauges. So, so in that sense, it's much more interesting.
Okay, thank you.
I hope that the fundamental behavior doesn't change too much, but you know, the higher the stress, the more energy you have, basically, the more strain energy you have to make a dynamic rupture. So it's probably much harder to stop the rupture at higher stress, right?
Yeah, but that doesn't mean that it's necessary for you to study the arresting part. You can still find, I think, important results, obviously. If you are looking into the patterns of how stress changes when the rupture arrests, I mean, I think it could be still reasonable for you.
You know, in the modeling study, what we did is we started with stress levels that were consistent with the lab, and then to get them to match the field, we pretty much just bumped it up by an order of magnitude. So instead of, you know, a strength of, you know, peak and residual at 8 and 6, we bumped it up to 80 and 60, and you know, we get the same results. So as long as this, you know, idea of like subweakening relationships between friction still holds at a higher stress, which we don't have any reason to believe it doesn't, a lot of this will translate to higher stress. The details may be a bit different.
So, Greg, do you have much control over the initial stress state? You talked about you need some level of stress heterogeneity if you want a rupture to stop, right? Is that something that you control, or just kind of happens? Whatever the geometry of the fault is controls mainly what the stress is on the fault? I mean, I should say the difference in stress at different fault patches.
Yeah, so what happens is we can control it a little bit. I originally thought we'd be able to, you know, just like put more pressure on some of these cylinders and less pressure on the other, and like basically define our stress distribution. But when I tried that on a smaller scale rig, I realized like that's a good recipe for just cracking the rock in half due to bending. So what we do instead is we try not to break the rock, but when we just first increase that normal stress, we get a frustrated Poisson expansion effect that happens. So basically the rocks want to, you know, push out laterally. And so because of the asymmetry of the blocks and the asymmetry of the boundary conditions, we set up a stress state where we get, you know, it's very favorable to rupture about 2 meters down, and it's very unfavorable to rupture about 2 meters down. We can't, it's really hard to measure it, but oh, it's not impossible to measure it actually. This is sort of what we think the initial sort of like shear stress distribution is. So we'll get a rupture.
Are you using your mouse right now? Because I cannot see, like, are you moving something over?
Yeah, I am. You can't see my mouse?
No.
Oh, that's weird. So actually we can measure the distribution of shear stress at least. That's on a different talk. And we can really see how it's much more favorably stressed basically down like 2 meters down the rock than it is earlier. So to answer your question, Thomas, we can sort of like, we have like some tricks. We have some loading procedures in our tool bag that we can use to generate a stress distribution, and we can like do it over and over again. Like we can come in and any day and say, okay, if we first squeeze it to this level and then load it this way, we will get ruptures that are here and confined to this location. Exactly why that happens is a complicated mechanics problem. So we can generate confined ruptures that are confined to the end that we're pushing on, and then the ones that are 2 meters down, like pretty easily. I haven't tried to do anything like much more complicated than that. Except that now that we have fluid injection, we can, we can initiate ruptures at different overall levels of stress too. We can measure with those strain gauges the distribution of stress. And this is kind of what it looks like for the experiments I was presenting today. The initial shear stress is much higher towards the end, towards the blue end, let's say, than it is. And there's even this one part on the fault where it almost seems like the strength is almost zero, or it's close to zero. Yeah.
So that's interesting. This is happened because you have a specific procedure on how you load the sample, and that's what you get as initial conditions, right? Those are the initial conditions I see here, right? And so the fault is highly pre-stressed when it's closed towards the end of your model. That's why it goes up, I guess, right? But from the other sides, right, much lower. Okay, well, that looks kind of heterogeneous here.
Oh, it's very heterogeneous, and we would never get.
On that one, you were pushing from the right, yeah?
Yeah, we're pushing from this end, actually. The reason the stress is so high here is because of an edge effect.
Right.
And because there's actually a little bit of net moment introduced. It's not symmetric, so we introduce a moment, so there's higher normal stress on the, the end we're not pushing on. I don't have a picture of it. Yeah, here it is. So basically, we're pushing here. It introduces a moment to this block, so it's a little bit higher normal stress on this end than it is on this end.
Can you go back to the previous? Actually, it's to 12:10. Okay, maybe I'll ask you later in our meeting.
Okay.
Yeah, so I'm not going to ask more questions.
Yeah, happy to chat a little bit more later this afternoon.